Today's Python course is on artificial intelligence, and I'm going to give just a very brief introduction to the course and to machine learning in general in Python, and then Joost will give a case study of how he's used Python and machine learning for a practical example in Deltaris. And then the rest of the session, we're going to see a few techniques that will hopefully culminate in a similar code to what Joost used to do some segmentation analysis. So this is what the schedule is. It's quite a tight schedule, and so the learning curve is going to be quite high today. So this is the introduction, and as I said, the case study. Then I'll show you simple neural networks. Clustering will be done by Carmen. Then we will have dinner at around 5:45. Then after dinner, we'll do some more advanced topics, which is convolutional neural networks and segmentation. And if we have time, there will be some time to discuss things at the end. So, what is machine learning? Essentially, these are algorithms and statistical models which perform an explicit task without actually being explicitly told how to do it. So it learns for itself relationships, correlations, inferences within the data in order to perform a task. So i.e. mimicking the processes by which we learn as humans. I've included this slide just to show you how large a topic machine learning is. So we have three key areas, which is unsupervised learning, supervised learning, and reinforcement learning. And this here is just some examples of what you can do with it. It's a huge topic. So the fact that we've got now roughly 3 hours, 20 minutes to cover as much of that as possible, just realize that we're only going to scratch the surface of this. And this is more of a taster course than an in-depth deep dive course. So what is supervised learning? There's two main areas of supervised learning. This is classification and regression. And in both these cases, this is where you have the input data and the output data. So essentially, you tell the algorithm, I have got these sets of inputs, these variables, and I've got these outputs. You learn the correlations, the functions in between the two to give me the most accurate response to those outputs. So this is known as supervised because obviously you're supervising the output. You're saying it must be this. Then you have unsupervised learning, and this is things like clustering. And this is where you just give it the input data. And for instance, you may say, I want this to be, I want this set of data. I want you to cluster it into 8 areas that are similar. So you would put the data in, and in an unsupervised manner, it would try to group together sets of data that are similar. And that's what Carmen will show you a little before dinner. And then we have reinforcement learning, which is essentially like, it's like playing a game. If the machine does an action, and then you either positively reward it or you negatively punish it for making wrong moves. So if you've heard recently about the AlphaGo and the chess algorithms that are beating humans, that's been based on reinforcement learning. And there's a lot of effort going into making these more applicable for physics-style problems, scientific problems. But we're not going to touch this area because it's a bit beyond the timing of today. So the aims of today, as I said earlier, is not a deep dive course, so this is more of a hands-on feel of machine learning techniques, and we'll do that via Python notebooks, so you can, the things we've given you, you can adjust slightly and play with the parameters, or even change the methodology within the actual course itself. And it's just so that we would hope by the end of today you're able to construct small-scale algorithms of your own with your own data using Python. What we will not be doing, and it was a prerequisite for this course, is teaching Python syntax or helping with Python in any in-depth way. Before Joost starts his presentation, within the file we gave you, there was a YAML file, and for those of you who know how to use it, you can install the required Python files using that YAML file in that way. Or you can open it as a text file and read the required things and do pip install or conda install for each one of them that you don't have.
Anyway, so for those who may not know me yet, my name is Joost Wieman, and I work at the hydraulic engineering unit in the coastal structures and waves department. So other than Jonathan and Carmen, I'm not an actual data scientist. I have a civil engineering background, and even I could do it, so it's very doable. What I want to talk about today is the use of video and AI, and in specific image segmentation, as measurement instruments in our physical facilities here at Altaris. I'm going to tell you 4 things. I'm going to tell you what it is, how it works, what we use it for now, and what else we could do with it, a few ideas we already have about the future. So, well, what is it? It's a new measurement technique making use of video imagery and using image segmentation, which is something that we'll also end the course with on how to do that. So, and what we essentially want to do is classify an image, or well, a video, a frame of a video, the pixels of that image into different classes that are meaningful to us. And in the context of physical model experiments, you see a picture here. Those classes are often air, water, stones, sand, or what have you. And if we're able to teach the model how to do that, we can analyze the development of those classes in space and time, and that leads to being able to measure wave heights, wave run-up, wave overtopping, the development of the sand bed, etc. So then, if you can do that, you make it into an actual measurement technique, apart from just the video. So that sounds fancy. How does it work? Well, as said, it's based on image segmentation, which is a machine learning technique we're going into today. And what image segmentation does is segment the image into different classes of pixels, which you, for instance, would also need for self-driving cars. So if you see here an image of a road situation, then a typical use of image segmentation is to train a model to be able to recognize the different components of this street, of this road. So this is, for instance, from a paper on an image segmentation model, and this is the result of the picture I just showed you. So it recognizes the road itself, the trees, traffic signs, lining on the road. This is the output of the model. It can recognize those different pixel classes. So we're not interested in roads, but in water and rocks and what have you. But essentially, our challenge is the same thing, right? We have this picture or this video frame, and we want the technique to be able to recognize these different classes. So in that sense, we can use these existing techniques to do this. And then we can use it as a measurement if we're able to link these pixels to real-world coordinates, to water depths and what have you. So how do you do that? Using a CNN, Convolution Neural Network. And also that Jonathan's going to explain later in this pizza course, so I'm not going to go into this very much on how this exactly works, these techniques, because that's going to go later. Apart from the technique, you need video imagery that's usable for it, right? So what we need for, besides the flumes or the physical models, we need cameras on those models. You can see here we did something with the delta flume, so then we mount a camera on the side of the flume. For the shelled flumes, they have glass sides, so then it's more easy. You can just put a camera next to it and film through the glass. Sometimes you need extra lighting, so you might need extra lights, or you might want to have a top-down view, so you mount a camera to look down. And to be able to convert from pixels to like water heights and real-world coordinates, you need some kind of markers that you know the position of in real world, right? Because otherwise it's just pixels. Well, for the shell flume, we've used stickers with red dots. In the delta flume, we've painted red dots on the side. And this is also the shell flume, and we painted red dots on the construction itself. So anything that is well visible and distinctive from the background environments, you can use as markers. So not really rocket science here. And then the fun starts, because then you have your video of your experiment, and then you want to train your model, because the model, these type of techniques don't really work out of the box, right? It's not magic. So what first you need to do is tell the model, okay, what do you want it to recognize? You need some kind of what they call ground truth to be able to train the model and learn how to recognize it. And in this application, the ground truth is a few examples of these images, and also examples of the classes you wanted to detect. So in this case, this frame is familiar or is similar to the one I showed you before. This is the shell flume. It's a construction of rocks. There's sand underneath. There's water in the flume, and air above it. And I would like the segmentation algorithm to be able to recognize air, water, two different types of rocks, and sediment underneath. So what I have to do to be able to learn that is to provide it a few examples of these type of pictures, and then also with these classes already in there. So indicating for each pixel, this pixel is air or this pixel is water. So how we did that is take say 100 of these images, take Paint or your other favorite image software, and draw green lines in it, separating the classes, and do that say 100 times. And for so these are frames. So this is just still frames of video. What we've also done is not training on the frames, but training on time stacks. So instead of X and Y, we did Y and T. So over time. Then I had in the image, I've had a regular wave height meter, and from that signal, I know the wave height at that point, and then I can annotate these time stacks, and then I have over the whole test for that specific point in space. Mm-hmm. I have kind of an annotation, and then I can train that and use that to analyze the rest of the image, so that you have for all the points in space have a prediction. So yes, we've also done that. Only for the applications that are not so easy to measure otherwise. That's not really an option, because if you look here, this is measuring wave height. So this is the height, and this is time in the horizontal. So here you could do that with a wave gauge. But for instance, this esoteric picture here is the delta flume. It is a top-down view of the slope of a structure, and then the run-up, the waves running up and down and up and down. And that's very hard to measure otherwise, so this is all painstaking work by hand, etc. If you have about 100 images, we've had already good results, so it's not that bad. And then it can analyze the whole video, so that's nice. So once we have this ground truth, right, these classes and a few example images, we're going to train the network. And to do that, we use like 75%, 80% of the images we have, and that's our training set. We feed that to the model, and the model has these images, it has the outcome it needs to reach, and then iteratively it will optimize the weights in the layers. We'll also come to that later when we're going into how the CNN actually works. And then the other remaining 20 to 25% of the images we keep as a test set, because then we can use the train model to predict these unseen images. So the CNN has never seen these images before, so you can really see, say to the CNN, let's do a prediction for this. You can check with your ground truth, like, does this make sense? Is the water indeed the water, or does it predict that it's stones or whatever? And then you have a model or a metric to see how well your CNN performs. And also very important, you can check whether your model is not overfitting on your training data. I think we'll also go into that a bit more later. And then, as you might have expected, this training is a computationally intensive and demanding operation. So you probably not want to do that on your own laptop, for instance. So what I often do is either do it here on the H6. Not sure what I'm doing, but I do it on the H6 or the Windows computational facility, or you could do it in the cloud at Amazon or Azure. But at least it's a good idea to do it, not do it locally often. And in terms of how it's implemented, it's actually implemented very similarly to what we're going to see today. It's in Python using Keras with either a TensorFlow or a Theano backend, and some OpenCV for the image manipulation. Using existing architecture, so the exact configuration of the CNN we just stole from somebody else, and also use pre-trained weights from somebody else to be able to train faster. Anyway, so this is a technique, and what do we use it for, or have we used it for up until now? Essentially 4 things: measuring wave height, bed level development, wave overtopping, and wave run-up in our facilities. And the facilities we've applied it to right now is the Scheldt flume and the delta flume, but it's not necessarily limited to those two. Those were just the projects where we could stick a camera on, essentially. So for wave height, this is essentially the input movie, and the pink dot is the output. Why only one dot? We were validating it, and the dot is exactly on the location where we already have a wave gauge. So we're checking the results from the video technique versus the results from the regular wave gauge to see how well it does. And this is, as you may recognize, this is our shell flume. So it's not a very spectacular video, but you can see that, well, the pink dot seems to follow the water level pretty well, so that's at least encouraging. I've analyzed this part of the video, so this pixel got that out, ran it through the model, and the pink dot is the prediction of the model of the interface between water and air, of the water level. But essentially I could have done this for every horizontal picture, every horizontal pixel in the image, so then you have a few thousand wave gauges. And you could say, well, Joost, why would I need a few thousand wave gauges? Well, okay, a few thousand is a bit much, but for instance, decomposition of incoming and reflected waves, you need 3, 4, 5 wave gauges. So in that sense, it is useful to have multiple without needing multiple physical wave gauges. And we did a little comparison. So this is in time, the time signal of the measured for the wave gauge itself in black, and the red for the deep learning model prediction. The figure below is the wave spectrum, which also matches quite nicely. And if you look at the spectral parameters, then wave height and peak period match quite well, and the spectral wave period is also reasonable. So, well, these first results are encouraging in that sense. So this is about wave height measurements. Then bed level development. So these are the pictures I showed before. So we were doing scour tests, also in the shell flume. So water, sand, stones on top of it. And if you have waves coming in, then the sand is going to do something over here. And it's very difficult to measure that while the test is going. Because usually you need to wait till the test is done, you drain the water, you get out the stones, and then with a laser scanner or whatever, you measure the sand bed and you know what's going on. Only now with video camera we were able to, during the test, film it from the side and then have a temporal development. So how does the scour develop in time underneath the stones during the test? Which is nice because we couldn't really do that before. And as you see, like, this is the after picture. There is indeed something happening. The stones, the sand is being scoured away, stones are sagging, etc. And then we could have these nice plots of the volume change over time, at least for the transect next to the glass wall of the flume. And one of the questions we could then answer is, okay, are we reaching equilibrium? So would the scour profile change anymore if we just kept on generating waves? And the answer is, well, that's not really equilibrium, it just keeps on going down, so that's important for the interpretation of these results. And why do this? Well, there's no real alternative right now, at least that I know of, to do this while the test is running. It's only before and after, and nothing during. And the nice thing is that it doesn't disturb the scour process itself, because it's all very sensitive with sediment blowing around everywhere, and you're not putting anything in the water, so that's nice. Then a small example of wave overtopping. So there it comes. There's a wave going over the crown of a dike. This is using a high-speed camera because the wave seems to move fairly slowly, but the high-speed camera is being played down a bit slower. And by kind of detecting the front and the top of the wave, we can detect the front velocity and the water vapor thickness, and then calculate the overtopping discharge. Which is nice because usually we measure overtopping just by looking at how much water goes over. But then you have all kinds of problems with sloshing in the overtopping tank, and you don't know anything about the front speed over here. So this technique gives you a little bit of extra information. What's the front speed? What's the layer thickness? All kinds of things that can be important for failure mechanisms, for instance, of tanks. And then my last example is wave run-up. So wave run-up is essentially like how far does the wave run up a slope. And we did that in both the delta flume, so that's what you're seeing now, and the shell flume, that's the next video. But as you can imagine, like the wave runs up the slope, and that's essentially, it ends up as a very thin water layer. It's also, there's a bit of variation over the width. So if you actually want to measure this, it's very hard. And that's also why these stripes and these numbers are on the slope, because the current way of measuring this, or old way of measuring this, I should say, is having two people there, one with a clipboard and a pen, and is writing down, and another one just looking at the stripes and calling out, so 46, 35, 51, just calling out the maximum run-up of each wave, which works, but is not very elegant, and it's very labor intensive. So in that sense, this is a nice alternative to have. And well, we also did this in the shell flume, as you can see. So it's nice. This is an easier method in that sense. But the nice thing is, if you from visual observation, you can only really say the maximum run-up level, right? You can't really say anything about the speed, unless you're very good at estimating the speed, but that's very difficult to do. And from this method, you also get the run-up velocities, which is, for instance, important for the stability of grass on the slope. The nice thing is, I'm going to skip this, it's not so important. So the nice thing is that you also see that it's not necessarily a straight line, right? This run-up, there's a bit of variation over the width. So what we've always been curious about is, are there wall effects? Like do these flume walls, do these affect the run-up and then probably also the overtopping? And well, we had all kinds of opinions, but no real data to support it. So once we had this, we were like, okay, well now we can look over the width of this slope, and let's look very close to the wall. Do we see a different behavior there? And then yes, for most tests we did see a little bit of more larger standard deviations near the walls. So that led us to believe that there is indeed some wall effects. We should look at kind of the middle of the flume and not so much at the walls. So say, yeah, if you leave out the sides, then you're probably okay, but don't extend your analysis. And kind of, we were already doing that with overtopping, which is nice. We only have the overtopping flume, overtopping shoot in the middle of the flume. So sometimes your hunch is correct, which is nice. So yeah, why is it actually, other than that it's cool and fun and stuff to do, why is it a valuable alternative? It's a non-intrusive method because you just film the stuff that's going on. You don't have to put in any probes, so you're not affecting the test results. And you can use it in times that traditional instruments just cannot be used. So, for instance, in the delta flume last year, we had willow trees, and those give a lot of debris, right, branches and leaves, what have you. So then it's difficult to use wire wave gauges because these twigs are getting into these wires, and it's kind of a disaster. So that's, in those kind of situations, it's a very valuable alternative to have. And as you saw with the wave run-up, that's just very hard to measure otherwise. So you can also measure things you couldn't otherwise. And at the end of the day, you need a computer, you need Python, you need a camera. That's not very expensive. So it's not your $10,000s of dollars of equipment spent. So in that sense, we were very happy with it. And we were thinking, okay, what else could we do with these type of techniques? It's in general, it's if you can see it well on the video, you can learn the algorithm to detect it. If you can see these different classes by eye, well, you're probably able to learn it. And the nice thing is that this CNN technique, this segmentation technique that Jonathan is going to learn you, is very generic. So in the beginning you saw, like, if you want to detect the street signs in the street or detect a wave, like it can do both. So that's a nice thing. So for other things we could do is we've now applied it inside in our inside facilities, but you could also apply it outside, of course, which is nice because having measurement instruments being placed outside is even more difficult because it's not that controlled circumstances, and a video camera is probably easier. So we could also do that, or the thing I would like to do myself, but I haven't been able to yet, is look, for instance, at the movement of vegetation under wave attack. So this is a video of a single, like, synthetic vegetation stem. But using the same technique, you could also just detect constantly where the stem is and then map the behavior of the vegetation. But anyway, there's a lot of other things you could do with it. These are just a few examples. But this is one of the examples you can do with the CNN segmentation technique. So I hope to have inspired you a bit.
This is going to be probably one of the quickest parts of the course, because this was meant to be 20 minutes. And so I've got to be done by, I think, just after 5 on this bit, so I hope you are okay. If you've got it on on the screen, it's not so good to read, so please read it on your laptop. So maybe blow it up a little bit. Okay. So we touched a little bit about supervised and unsupervised, so I'm going to skip past that, but predominantly neural networks are supervised, in that what you do is you give it the inputs and you give it the outputs you expect, and in those inputs and outputs we then try to formulate the function, essentially, between the two. To dispel the myths that neural networks are some all-seeing black box, they're essentially the lazy man's version of regression. We don't give it a formula, instead we throw loads of neurons, which I'll show you in a moment, at a problem, and they automatically work out, or try to work out, these complex correlations and structures between the input and the output. Whereas traditionally in regression you would give it a formula or the structure of a formula and expect the coefficients. Here we're just playing with the weights between neurons. So the first thing is these are the things that we are trying, the libraries we're going to use, and for the reasons we're going to use them are there. So if you guys can press play on this notebook and just double check you have them all, so you can run through this, that would be a good thing. Okay, and I'm going to try and get everything on the screen at the same time. So a neural network tries to mimic what happens in our brain. Our brains work with essentially synapses and neurons, and what happens is that when that neuron is stimulated by multiple inputs, it fires, and it fires a particular strength or even a binary output. But it fires it fires an electrical impulse. So that's what it looks like in biological terms. And our brain is essentially many of those connected together, many billions, maybe trillions, I'm not sure of the number, but that's essentially how we operate. And so as computer technologies have advanced, because neural networks were a very old concept, they've been around for 30 or 40 years now. As computer power has increased, we're able to create systems of very large amounts of these and very large amounts of data. Because if you imagine how we learn as humans, we learn by taking in a stimulus and over time, we work out how that stimulus goes to a reaction we make on the outside world. So, what are these? So this is essentially the structure we make of a neural network. These are the circles are what's known as neurons, and between it we have the I think it's called synapses between them, and those are the weights that we can adjust. So here the yellow circles is known as the input layer, so that is your data that you take in, and then we have hidden layers which manipulate this data and then pass it on to the next layer until we get to an output. So each of these takes a weighted input of all the other on the previous layer, and then the synapse, which we'll see in a moment, or the neuron, has a particular what we call activation function. And what it does is when it takes that information, it goes, how do I convert my input into one single output? and it goes through, and this is the forward direction, feed forward. And the way we train is what's known as back propagation. So we have the answer we want in the supervised, and we update the weights all the way through back to the input. And it's something I don't think you guys need to know about how that function works, because in most implementations of neural networks now, that's done automatically for you. So I think that's a bit beyond this course. All you need to know is that these connections, so these are your inputs, and each of the black lines has a weight, and the training process is changing those weights until you get the output you want on this side. And each of these neurons has an activation function which says, whatever my input is, my weighted input, this is what I'm going to do with it. And those activation functions are quite simple. So this is a neuron, for instance. It takes all its inputs in, and W1, 2, 3, all the way through to 4, or however many you've got, are the weights. We also add what's known as a bias, just to say that there are some things we're not so sure about. So that's a bias there. And we sum these together, and then it goes into some function, the activation function, which outputs another value. And that essentially is the neuron. And those functions are very important, and so I go through them now to do so. Yeah, just briefly here, there is a glossary of terms as well that you will see that get spoken about a lot. In the training process, when we update those weights, it's back propagation. And we have terms such as epochs and batch size. And what they are is the number of times we allow the algorithm to see the full data set. So if you say we use 200 epochs, that basically means it sees the data 200 times in its training method. Batch size is how big, how many times it sees all this data before it updates the weights in its system. And then there's the loss function, and the loss function is how you measure the error between reality and what you predict. And then there's the optimizer, and the optimizer is how the back propagation algorithm searches for the right answer. Because if you can imagine, it's trying to minimize the difference between its prediction and the actual reality that you feed it. And that's how it trains. And there's several of these optimizers, but you don't have to worry about them because most of them are, again, provided for you in by these libraries. Then occasionally we'll talk about hyperparameters, and this basically is a combination of all these other terms and data that we feed in, such as number of epochs, batch size, error properties, learning rates you'll hear. But those are kind of beyond this course, and as you get familiar with this in hands-on terms, you will learn those. So, as I said before, a neuron is essentially an activation function, and this is the sum of the weights times their input value plus some bias, and that's what the activation function is. And we have a number of them which we commonly use for each neuron. So if you look through this list, there's one known as the sigmoid, and what that is this curve between 0 and 1, and it's centered around 0. And what this means is that during the learning process, this gets stretched and manipulated so that it can say, right, values above a certain value, I always give 1 of. I always pump out some value of some high value, and other values lower, I pump out 0. And this is kind of the traditional activation function that we typically use. But you can imagine that if you try, once this is trained, if you try to use values outside the range you trained it on, you'll just get a maximum and a minimum. It won't work. So this is typically what we say about neural networks, is that they are trained on situations that is more of an interpolation than an extrapolation. They're not very good at extrapolating. They can do sets of circumstances that combinations of circumstances that it's not necessarily seen before. But if you extrapolate those circumstances, so it's outside the range it's been trained on, it will try to give you a good guess. But you can see in such activation functions as this one, the output of this is going to be constant outside the kind of working range of the data. However, that said, occasionally you do have processes where you actually want that functionality as well. But then we also have lots of other activation functions. This one, the tan H, which does go between 1 and -1. Similar analysis, similar functionality. Equally, you can say that your problem is a linear problem. You've not got scaled data. But you want to try it with a combination of linear. You can describe your problem as a combination of linear functions. Then you can use the linear activation function. So this neuron takes a value and then pumps out a value that is, pumps out its sum of its weights, essentially. This isn't really that important because most of us actually just, in some situations we have a gut feeling which of these activation functions we're going to use, but in other situations we just try them all because you don't know which ones will work the best. So I'm just using this just to show you that there is a collection of activation functions, and over time you will get better at using them. You can see this last one, ReLU, which basically says things can't be negative. You can say that for things in nature, for instance, you won't find things that follow a log normal trend are not going to go negative. So you would say, okay, then I want to use ReLU. And typically you also say you would use a sigmoid if you want to have binary decisions, because you've got 0 and 1. So for instance, if you're saying you're trying to, in the pixel classification, if you've got 2 choices, or you've got multiple choices, but it's a choice between, it's binary choice, or even just multi-choice, then you want it to be trained with 0 and 1. And that slope in between becomes, okay, I'm not quite sure. I'm 70% sure it's a 1, or I'm 20% sure it's a 0. So there are certain more classification style that you can be definite with. And you would use linear if you're just doing a very standard regression, and because the idea is that if you use enough linear activation function, like linear neurons, collectively you can describe any function you want. Normally, it's very, very good practice in when doing neural networks that you scale your data between 0 and 1, or in the case of if you're using tanh, between -1 and 1, because then the learning process is a lot faster and easier. But if you use, technically the backpropagation algorithm should find the optimum solution regardless of what data you put in there, but the weights become a bit crazy. So you want to kind of get out each of your features between 0 and 1 preferably, because that helps the learning process. There's lots of other reasons behind it, because it would always be high, or because you've got huge figures in there. So that's predominantly why we scale. And there is another activation function that's quite important, which we use when it is for that we want probabilities, and that's called softmax. And the reason we use this activation function is that it conveniently, the area underneath it adds up to 1, no matter what you put into it. So the range of data you give it will conveniently add up to 1. So therefore you can get probabilities of something occurring. And so when it's a probability output you want, we tend to use the softmax one. Okay, I've spoken briefly about optimization algorithms, but that's basically how it finds that minimum, that difference between the two values, or between the prediction you've made with your network and the reality. And from that it backpropagates and changes all the weights via gradient descent algorithms and things like that. And these are the typical ones you would use. We will probably see predominantly today Adam is the name of the one we use. They've each got advantages and disadvantages, so again it becomes kind of, you get a gut feeling for your problem which one you're going to use. Okay, loss functions. You can imagine the loss functions. These are just all the ways of measuring the difference between your reality and your ground truth and your prediction. And so we tend to use, well, you've got to use categorical ones when it is a decision or it's a grouping, and then you use like mean squared error when it's a regression style technique. So we're going to start with a very simple example, which you guys can manipulate yourselves if you are up to this point. We're going to create some noisy data, so with a straight line. So here I create some like a random uniform variables. I take between 10 and 14. So I'm taking some values between 10 and 14 in this line. I've created this 23.3 and 5.5 equation, and what I'm going to do is add some noise to this so it's not just a perfect straight line, and I plot it here, and we get a very simple almost linear line with some noise. If you zoom in on that, it will be very noisy. So we've got that, and we're going to build a Keras model. A Keras is a library. It's a high-level library which kind of covers and wraps TensorFlow, which Yo spoke about, and Thanos. And what it does is it enables you to very quickly and easily build a neural network to do your problem. You just have to provide it with the input and the output data, and tell it that what each layer is going to, what activation function each layer has, and it builds the model for you and trains it as well, which is very good. So here we're going to say we want a model. In this case it's sequential, which is the easiest form of Keras. That just basically says each layer is going to have the same properties, and it will connect to the next layer sequentially. So in this case, I just say I activate that, and then to my model I add one single layer, which has one dimension. We're only putting in, we've got x, and we put in y. So that's our data set. So we put in one, so for every x there is a corresponding y. And here, because it's a linear, we can see it's linear, I'm going to choose an activation function of linear. So what I expect, what I put in, should have a linear relationship to what I get out. So everyone understand what I'm doing. I'm putting into a single neuron one input and getting an output. And what I'm going to do is adjust the weight and the bias. So you can imagine the weight is the, so this is y equals mx plus c. So the weight is that m value, and the bias is the c value. Okay? And so what I also then say is I want to, so I've got to compile this model to put it together into a functioning model, and I'm going to use the mean squared error and the optimizer Adam. Okay? Now, what we also have to do is split up our data, because there's a phenomenon known as overfitting. And what overfitting is when we fit precisely to a situation. So it doesn't matter, it can't be used for anything else other than that situation. If we give it data, combinations of data we don't have, then it won't work, because it's so highly fitted to that. In fact, it would fit the noise almost if we did that. So we had an example, I think it was yesterday, where we had data that we knew we had errors in, and we got 100%, even though there was errors in the data. The mechanism had found, the algorithm had found correlations that couldn't possibly exist in physics. And so that's called overfitting. And so to combat that, one of the things we do is to split our data set into training and test data. So we train on one and then test the result on another. In this case, it's called the training data, and the validation data is what we also know it as. So this here is just splitting our data. I've asked for 80% of it to be training, and so of those 2,000 points, 1,600 of them will be training data, and the rest will be test data. And I've just plotted it on the graph below. Then I've run this test. It takes, to get to a reasonable answer, it takes over 2,000 epochs. So I'm not going to run it, you guys can if you want. It might take a while. And then what I see is, I see that it's almost got to convergence, the result. I look at the history of this, the history of the loss, which is the loss in training, in the training data, and the validation loss is the loss in the actual, that validation portion. So basically on the first epoch, when it was initialized and when it did its first kind of calculation on, it said, it went through all the data once, and then all the weights had been adjusted, but when it did it, it had a 80,000 mean squared error. And then by the time we got to here, we were approaching 0. It was probably, I think it was about 11 in this case. But you couldn't get it much closer than that, because you can see it's actually, it's only just got to the convergence state. And from that, what I do, I ask for the model summary, which shows you kind of the structure of the neural network. And then I ask for the weight and the bias. And that weight and the bias, remember, it was the m and the c in an mx plus c equation, and it gives me these two. So my bias is a little out, but my my gradient is approaching quite nicely. And what you can see I did in the later graphs is to generate, to call a prediction. In this thing, you ask the model to predict with an input value, in this case 12.2, and I get the difference between what the function I originally produced was and my prediction. And equally here, we will You can see the line, the gradient slightly out. Probably the intercept is not the best, but we can do that. Okay, we'll go till 6 o'clock before we eat. So I've got 10 minutes to do the second example. So this example isn't really so practical, because you could obviously, it wouldn't take you 20,000 epochs to draw a straight line through some random data. But this next exercise is a bit more, yeah, you guys can, I think you should in time do the exercise I've written there just to play with these values and see what you get. But the next exercise is not so simple. It's this is a set of data coming from a place in India, or people with a particular heritage in India who suffer from diabetes. It's apparently very prevalent in female populations in India, and basically we look. We have a data set where we've measured these values, i.e., how often they're pregnant. I have no idea what triceps skin fold thickness is, but those are the data that somebody's come along and said are important to test whether someone's diabetic. Okay, so we have this data set, and you can load it. We load it in here. I assume you're all familiar with pandas. Yeah? Ish. Okay. Anyway, when you load a CSV file into pandas, as long as it's got the right headers, those headers become your parameters, your variables in the thing. So you can ask the data set the information, and it tells us what information we have in this data set. So we have all of those, but they're all in the form of either integers or floats. So it's all numerical data. And we can visualize that in what's known as a pair plot using the package Seaborn. And what this helps us to do is to look at the correlations between the various parameters. So this end column here is whether someone has diabetes or not. And these are the parameters we had. And you can see that, well, there doesn't appear to be any real correlations between those things. So the combination of every column, that's why you see this along the diagonal, because it would be a straight line. Yeah. But what this is giving you is a breakdown of that particular, how balanced your data is. Yeah. Because ideally what we want in all data science is we want a very balanced data set. We would like there to be, all of these to be almost straight lines, so we have equal amounts of every possible combination. We clearly don't, and so we're going to do the best we can with this data set. So in this particular data set, our output data is the diabetic, whether you're diabetic or not. So it's a 0 or 1, whether you're diabetic, and we have the rest of it is the input data. So this pop term, actually what it does is it removes it and puts it somewhere else, that column. So we have diabetes in our output data. Okay. And we have input data as the rest of the data set. And you can see now, if we do a summary of it, that that diabetic has gone from the list. And we have 268 diabetics. The rest of the data set, the other 768 are, so 500 people don't have diabetes, 268 have diabetes. Because I did that sum of that column. It's either 0 or 1. Okay, so that gives us some impression that we haven't really got a balanced data set, because we've only got half of our people, a third of our people have diabetes. So we have to kind of be aware that this isn't not necessarily the most reliable analysis. Okay, the model here is a bit more complicated. So we set up the sequential model again, This time we're going to have a layer of 12 neurons, which take those eight parameters we have, and the activation is going to be sigmoid. So, because if you remember rightly, this is a 0 or 1 decision. So it's going to be sigmoid. We're going to add just because I know, I'm going to add another layer, which is going to take, again, we're going to have another 8 this time inputs. So all of those 12 go into all 8 of those nodes, those neurons. And again, it's going to be sigmoid. And my output layer, because I want one answer, I'm going to have 1. What it means is that you can imagine the function kind of needs to be manipulated a bit. It has maybe 2 stages to it. But the thing is that you've got 2 things you can imagine. There's 2 ways you can do things. You can either make a bigger layer or a deeper network. And so those 2 you often play with to try and get the right balance. Because if you have a bigger layer, essentially those 2 layers can be, instead of parallel, can be like that. And the weights will be adjusted here. And so often you just play a little bit until you get there. I'm just trying to show here that you can have 2 layers. Most people find that 1 is sufficient, and I think there's a very famous paper that says 99.9% of all neural network problems can be solved with 1 layer. But I'll try and find the paper. So it's not me, that's a quote. Okay, and then, as I said, the final layer has to be, that's the output, essentially. You always have a final layer, which is the output. This has to be the number of layers, this has to be the number of results you have. So in this case, we have 1 result, which is 0 or 1. Does that person have diabetes? Okay. Then I compile it again, and this time I compile it with a loss function that has to be cross entropy, because it's a categorization analysis. And I choose a binary because we've only got 0 or 1 group. Again, I'm using my optimizer Adam, and this time I've used this metric accuracy. It's the metric called accuracy is a bit of a difficult one because we also have loss. Now, in a lot of these libraries, loss refers to when you have a regression problem. So loss, the difference between A and B is mean squared error kind of loss. But the accuracy is how often am I right? So this accuracy means how often have I predicted a 1 and got a 0 or a 1. So how often I get the 1 essentially. So if I get the right answer 100% of the time, then that will be 1, the accuracy. So that's where you've got to be careful of. Loss and accuracy are 2 different things in machine learning. Okay, so I now compile it, and then I do my training, and the training that does all that back propagation, and I should have said that in the last example, is .fit. So I give my input data, my output data, and the number of epochs, and as I said, the batch size, so that's how often it's going to update its weights in the network. What you should see here is that I've used the entire data set. Now that's bad because, as I said about the overfitting, but I only have 768 points. I'm not about to make it, if I cut it incorrectly, I could potentially cut most of the diabetics out of the analysis and everyone would be free of diabetes. So in this case, I've used it all. It is bad practice, but when you have such small data sets, you often have to do that. So if you run that, and I don't know whether any of you did. So when I look at it, I can see, as I said before, my loss goes down, because this is the loss based on a numerical assumption between 0 and 1. So when it predicts 0.11, it's, that adds to the loss. And this is how often I'm right if I kind of choose a more binary approach. So that goes up, that goes down, I'm really happy. So So if you can also use this term evaluate model with input and output data, and it just gives you the accuracy as a number. In this case, I got around 79%, but it's some people on my course last time got it in the 80s by just playing with the hyperparameters. Then we look at, in this term, we're looking at how often our predictions are correct for each individual case. So this is the number that comes out on the prediction. So what I'd like to say to you is this algorithm is basically saying this person here is, I believe, 89% certain that they would have diabetes. But that, because it's 0.89, so above 50%, it goes to the 1. If it's below 50%, it goes to the 0. But essentially, you can think of that as a probability. The closer that is to the 1, the more certain the algorithm is that that person would have diabetes. And if you look through it, it's reasonably accurate. In fact, in this case, 79% of the time. Oh, sorry, so this one is when so this is what the algorithm gives us, the output. This is the rounding up or down.
Okay.
And this one is what the ground truth is. This is what was in the data, whether it was a 1 or a 0. Another thing you will get a lot of from in all of AI is what's known as a confusion matrix. Do you all know what one is? So basically, this is, I've predicted 1, and the algorithm predicted 1, and that's, so these two are false negatives, and false negative, false positive, positive, whatever. You know what I mean? Those are correct. Those are incorrect. And so when you have a big confusion matrix, you expect the diagonal to be very strong. And everything off the diagonal, you hope to not be so good. So when you have multiple classes, multiple classifications, multiple outputs, you would have, a big one, and what you want is the narrowest diagonal you can possibly have through the confusion matrix. So this is the code for producing that. I've just asked for a binary style coloring, so it's easier. I'm not 100% sure what I did with that next bit.
Normalize it, right?
Oh, yeah.
2 percentages.
I just ran my code. I got like 81% accuracy. But why
Me as well. So
why is
it's
that?
not-
Why is there?
Because the
I
start,
way worse.
the start of the code is random.
Yeah.
As a random number. So we could all make it the same for each of the same machines by setting a random seed at the very top. But if you run it again, you won't get the same answer. And also, be very careful with these notebooks, because if you keep pressing fit, if you keep pressing play on the fit one without resetting it, you're essentially using far more fittings than 2000. You can just keep pressing it and you'll get a lot more. Okay, and one little thing, so reproducibility, what we've just spoken about, is at the bottom. And one other thing I wanted to speak about is the baseline error, because you've got 81%. Now you need to know how good that is. And so it's very important that you get a baseline error, because it's not 50-50. It's clearly not 50-50. So what we tend to do is go to statistics, and we say, okay, if we predict the thing that is most likely to happen all the time, what would be the accuracy? And so in this case, we had 500 out of those 768 didn't have diabetes. So that gives us 65.1%. So if I always predict that you're not going to have diabetes, no matter what the data is, I will be right 65% of the time, according to the statistic. So your 80% means that, we're actually improving on standard statistics, and our algorithm is worthwhile. It is. I have seen these numbers go significantly down, and still people claiming that there's a published paper that said they got an accuracy of 82%, but the baseline error was 100. The baseline accuracy was 100% because virtually nothing changed in the system. So you see, you've got to be very careful about how you measure things. And so what's very important is that we don't steer too far away. We're not going to shove all our data into the system. We shouldn't do. And we should adjust the raw data for our domain knowledge. Secondly, we should also, we then have a validation and cleaning process where we say, okay, so a bit like Joost was speaking about having clear pictures with lighting correct and things like that. That's the equivalent of trying to get a clean, valid data set. And so what we try to do is we should look at these pair plots and kind of start looking, well, it's imbalanced, there's missing bits of data we don't have. We should, if two things correlate together very highly, then you shouldn't put them both into a neural network or into any methodology that does this thing. Even regression you shouldn't really do with two highly correlated things, because they're essentially the same thing. So you must look at these and be very kind of brutal about how you deal with it and use your domain knowledge. And 99% of your time, I would say, is getting the data, cleaning it, validating it, adding your knowledge to it. These techniques, there's a piece of software called Vecca, which you can get which will do 90% of the things you want it to do. The image stuff, no. But the rest of it, even MATLAB, you can do the same thing in MATLAB. The things in the background are there already, the engines. All it requires is someone to come along with a data set. And so that is where we come in as Deltaris and with our knowledge.
Okay, so for now, John was discussing about neural networks, and as he said, that method is used in supervised problems. But clustering is about finding hidden trends in your data, trends that you even don't know, and you forget about any labeling. So sometimes people tend to get confused between classification, which is a part of supervised learning, and clustering. So classification, as John said, is when you want to classify diabetes and no diabetes, or if it's a dog or a cat. That's classification. But in clustering you might have or might not have that label, and you want to just figure out that. So let's assume that you have a store of fruits, that you are selling fruits, and you want to predict, okay, from the size and from the color and even from the texture or the smell, I don't know, then you want to classify whether a fruit is an apple or an orange or a banana. But a clustering is, okay, let's forget, I don't know whether a fruit is an apple or a banana, but then taking into account the color, how it smells, the size, I want to infer whether it's an apple, a banana, a kiwi, whatever. So this is clustering. So since clustering is very useful to get hidden trends in your data, it can be very useful for different problems within Deltaris. So here I am just going to mention a couple of them. So for instance, in ecology, a lot of ecological data sets are prone to have a lot of uncertainties. So you can use clustering, for instance, to unveil hidden correlations between your environmental variables and a certain type of organism. So as an example, this is taken from the literature. Some guy, Miguel Kiwa, used clustering just to infer how how to get different vegetation types given some ecological environments of the region that he was studying. That's another paper that was studying similar things but in the Amazonia. In water quality also, clustering would be very important. For instance, you can evaluate the impact of wastewater discharge in a certain area, or which combination of factors influence to have polluted or non-polluted water. And maybe you want to study that in an area that is unfamiliar with you. So you just take the data and then you just let the algorithm infer those relationships. That's another paper related to that topic, but it was used in India. And in geotechnical engineering, for instance, clustering can be very useful to characterize the subsoil types or the types of subsoil without using the Robertson charts. So actually that method has been widely used in the literature. This is one example, and this is another one. So as in supervised learning, we have like a lot of zoo of models. Neural networks is one of them. In clustering also we have a lot of different methods. Here I'm just going to explain the three most common ones. And of course they have some advantages and disadvantages. So let's just first start with k-means. I don't know if the video is going to, no, okay. Never mind, this was a video. So basically in the k-means, let's assume that you have three clusters. Of course, most of the time your data is not going to look at this, like you are not going to get very nice clusters, but okay, this is an idealistic case. So basically what k-means does is that first you need to initialize with a certain number of clusters. So in this example you say, okay, let's start with 3. So basically the algorithm is going to initialize the center of the clusters at random, and then it's going to compute the distance of each of the observations. Each point of here is an observation in your data set. So the algorithm is going to compute the distance of one of the cluster, or the distance between the cluster center to each of these points. So for instance, this point, if you have a cluster center here, and another cluster center here, and another cluster center here, for instance, this point, the distance between this point and a cluster center here, will be the smallest one. Will be smaller than the other two clusters. So this point is going to be classified as being part of cluster 1 and not 2 or cluster 3. So this process is repeated for each of the points in your data set. And then the cluster distance is recomputing by taking the mean distance of all its members. And of course you can infer that the center of the cluster is going to change every time. It's going to stop, the algorithm is going to stop until the cluster centers, the position of the cluster center doesn't change that much. The k-means algorithm is used a lot, but as all algorithms, it has some advantages and some disadvantages. One of the disadvantages can be visualized in this plot. So let's assume that you have two clusters which don't have a nice shape, or doesn't have a symmetric shape. So for instance, this cluster, you would see that these points of the outer ring belong to one cluster, and all the points that belong to the inner ring belong to another cluster. But if you use k-means, this is going to be the classification, which is incorrect. And why is that? Because k-means fails when the center of the clusters of two different clusters are very close together. So the k-means just get crazy, as you can see here. The other disadvantage of k-means is when you have a non-symmetrical shape clusters. This is this case. So for instance, here you have like one cluster with a banana shape, another cluster with a banana shape, but here the k-means fails completely, and it's because it doesn't have a symmetrical shape. This is one of the disadvantages. Another disadvantage is that you can imagine that if you have a large data set, and large I mean maybe more than 10,000 points, observations, then this algorithm is going to take a lot of time due to the computation of the distance of each point with respect to each of the clusters. And another disadvantage is that you need to specify the number of clusters in advance. And this is very bad, because if you don't know how many clusters you have, how on earth you are going to put that as an input for your model. So this is a big disadvantage. But for apart from that, for the small data sets, then it's good. In the Jupyter notebook, we are going to see a trick to get a number of clusters, but just as a parameter. Another algorithm that overcomes the disadvantages that has the k-means is this clustering method, the DV-scan. So basically, the DV-scan, what it does is that it selects a point. So let's assume this is your data set, and it's a nice smile face. I don't know if you guys are able to run the movie in your a local copy of the presentation, but basically the algorithm is going to select one point at random, and then you need to specify an epsilon, which is a distance around that point. So the algorithm is going to say, okay, all the points that are within that epsilon radius are going to be part of the same cluster. And then the algorithm is going to just run through each of the points, and then all the points that are close together are going to be labeled as the same cluster. Now, for instance, now the cluster goes here to one point over here. All the points that are within the distance of within radius epsilon of distance are going to be classified in the same cluster. But since these points are very far from these ones, these points belong to another cluster. So in this way, you are able to cluster points that doesn't need to have a really symmetric shape. So just this algorithm is much better than k-means. The advantage of this code is that you don't have to specify the number of clusters, but now you have to specify the epsilon, which is very tricky. But apart from that, then the nice thing is that then after running your code, you are going to have the number of clusters that your data has. And then with the number of clusters, you can analyze in your data set how the features behave. So maybe you can say, okay, all the points that belong to this cluster, all the apples, I found that has a size between, I don't know, 0 and 3 and 13 centimeters diameter, for instance. I don't know, something like that. Yeah. Another disadvantage is that, for instance, if you have a data set with a lot of features, then this algorithm is not that good. And why is that? This is something for you guys important to keep in mind, and is that the more dimensions you have in your data set, dimensions means features, the more scattered the data points are going to be. And that's a problem for data science because your question, if you throw up that data set in your algorithm, then it's very hard for the algorithm to find the real trends in your data. So that is a problem, a generic problem for clustering algorithms and also for supervised algorithms. So it's important to reduce the dimensionality of your data. Also for clustering. Okay. Another clustering method is called hierarchical clustering, and this method is, well, I really like it a lot because works in this way. So first, let's assume that you have these points. You have a data set with 5 points and 2 features. So the hierarchical clustering first assumes that each point belongs to one cluster, and then searches or computes the distance of each point with respect to the other ones. So then, all the points that are close together are going to be part of one cluster. So first, you start with 6 clusters. Then in this particular example, 0.6 and 0.5 are very close together, so they belong to one cluster. Then that cluster is very close to P4, so it's going to have, these 3 are going to have one cluster, and so on. The same happens with these points. The algorithm stops when you have only one cluster for the whole dataset. So in this case, well, this is how the hierarchical clustering works. What are the well, depends on your point of view, that can be an advantage or a disadvantage. In this case, you can have different types of clusters. So depending on what you want to answer, you can say, okay, I want 3 clusters or I want 2 clusters. So then you can specify the number of clusters, specifying the meaning that, okay, in the result you have certain you have this hierarchical clustering. So you can say, okay, let's assume in a water quality problem, you want to study what is the relationship between polluted, or what are the driven factors between having polluted and non-polluted water. So in the hierarchical clustering, you can say, okay, what are the conditions such that I have 2 clusters? Because here you would have 2, 6, you would have different clusters. So, okay, what are the clusters, or what are the conditions such that I have 2 clusters? So I have 2 clusters, I can go back and link those 2 clusters with each of the observations in your dataset. And then you can know what are the factors between polluted and non-polluted water. But if you want to say, okay, no, I don't want to have a binary decision. I want to study, okay, what are the driven factors between having polluted water, neutral water, and more or less polluted water and clean water. So in that case, you would have 3 clusters. So then here you look at, okay, in the algorithm, which are the decisions such that I have 3 clusters, and then you link those 3 clusters with your data. I don't know if that's. So while in the k-means, you just set the number of clusters as an input, and you get as an output that number of clusters. Here you can have like different number of clusters, and then depending on what you want to see, then you can say, okay, I want 2 or 3 clusters or 5 clusters. So advantages is that well, this algorithm is not sensitive to the choice of distance metric. As you can see, for k-means, we needed to compute the distance between the cluster center and each of the points. And dbscan, well, we were using an epsilon radius, but still, we needed to get distances. Here, we don't have that. This has an advantage because then you would have like an hierarchical selection of clusters. So then you can visualize your data set from different points of view. Okay, so here is a comparison of methods depending on different clusterings of data sets. So here you have the k-means. Mini-batch is an implementation of scikit-learn of k-means. You can have two implementations of the same thing. The normal k-means, which is very good for small data sets. If you have a bigger data set, then this is like an optimization, just to be able to run the same code but faster. So it's called mini-batch because a backend it just selects batch of your data. This is the hierarchical clustering, and this is DBScan. So basically, you can see here that if you have this data cluster in this with this shape, you see you know that okay, the agglomerative clustering here and DBScan is very good, both of them, but the k-means not, as I showed you before. If you have data set like this, organized like this, clustered like this, k-means fails. But again, DBScan and clustering doesn't fail. So I would say that yeah, it's better to use these methods because, of course, in clustering you don't know how well. Depends. If you know how your data is structured, then you can use k-means. But if you don't, which I would assume that is most of the case, because that's why you want to go for an unsupervised learning thing. Otherwise, you would do supervised learning. Then it's better to use these two techniques. But now you can see that if you have data like, for instance, data like this, that is really messy, this is a more realistic picture, you plot your data and you just see just a bunch of points without any like a structure, then k-means might work better than these two. But this is, yeah, that really depends on the data. Okay, so please guys go to the notebook. Oh yes. Oh, okay. So basically, here, just feel free to run it. So for this exercise, we are going to use one of the datasets that are already in scikit-learn, which is the digit dataset. That dataset contains 1,700 samples. Samples means images, number of images, and each image contains has a size of 8 × 8, meaning that each image has 64 pixels. So we want to use clustering in order to know which images are the same. So you can first, so the advantage is that is already ready the dataset. So basically here we are going to see the dataset from 2 points of view. First, the real images, and second, how those images would look like in a real dataset that is an input for the clustering algorithm. So this is the dataset here, the digits.data is the dataset, the input for your clustering algorithm. So what is this? So each row here, or each observation, corresponds to one image. And since one image has 64 pixels, each pixel is thought as a feature. So in the end, you are going to have a dataset or a table that contains the number of images times 64 features. And what you have here is just the intensity, the brightness. Oh. So this is the input of the for the clustering. Now, this is just a subsample of that set. These are the images. So each image contains 1 digit. And as you can see, the digits are very blurry and very terrible, which in our case is good because we really want to test the capabilities of a clustering. So what we want to do here, so the original dataset has a label per image, meaning that this has a label of 0, 1, 2, 3, 4, 5, so on. Is from 0, the number of digits is from 0 to 9. So you can say, okay, you can say, okay, I want to predict if you would want to build a supervised learning. The question that you would ask would be, okay, given an image, I want to classify which digit it is. But we don't like that. We want to say, okay, from the pixels, I want to know which digit it is. So we are not going to take into account the label. So if the cluster algorithm is good, it should be able to have, or each cluster should correspond to 1 digit. You know, we have the target, the labels, but we are not going to use that. So in principle, we want to achieve a clustering, or the clustering should be able to say, okay, one cluster should correspond to 0. Another cluster should correspond to 1. Okay? So for this, we are going to use KNN. And remember that for KNN, you need to specify the number of clusters. Here you would say, yeah, we have 10 digits. Let's put 10 as a number of clusters. But in reality, you don't know how many clusters you have in your dataset. So how can you get the number of clusters? Okay, I'm going to give you here one trick. There is a trick called elbow method. And the elbow method, what it does is just it looks at the minimal distance within intercluster distance, meaning that you are going to specify this. This is the distance of each point within the cluster. So you can say, okay, for one cluster, if I assume that my data set has one cluster, would be the distance of each of the points with respect to the center. So if you have a single cluster, that intercluster distance would be very high. But then if you add or put more clusters in your data set, that distance is going to be smaller because the clusters will be smaller. So at some point you will have, if you plot the number of clusters versus your distance, you are going to have something like this. A curve that is going to converge towards one distance. Doesn't have to be 0. Well, yeah, should be 0 if you put that each point belongs to one cluster. But you will notice that at some point, this curve is going to go down very slowly, meaning that if you put a lot of clusters, you are not going to gain that much in this variable. So that sweet point is the one that you use to say, okay, this is the optimal number of clusters. This method is very empirical, but somehow works. So in this case, you can say, okay, here the variation is quite big, but it's getting smaller, the variation among points. And here you can say that this variation, doesn't change that much. So you can say, yeah, well, let's put 10, you could put 9, you could put 11, but yeah, let's put 10, okay? So what we are going to do is that, okay, we know the number of clusters that we want, so we just use k-means. Here, these k-means, we are using scikit-learn, scikit-learn has a lot of clustering techniques. The ones that I explained to you are already implemented in there. So the way in which you called k-means is just by this. You here specify the number of clusters, and since maybe just for reproducibility, you just fix your random seed. And then you fit your model with your data. So then, note that we have 64 number of dimensions. So in the end, you fit this, and you are going to get 10 clusters, which is your number of clusters, times, and this is each center of the cluster, and each center is a vector in the 64 dimensions, which each dimension is 1 pixel in your data. So let's visualize each of the clusters. These are the clusters. So you can see that one cluster contains 1, the other cluster contains this, the other cluster contains 6. This is something blurry between 8 to, I don't know, but okay. So you can see that, okay, somehow picks up some numbers. But here is something. This cluster doesn't mean that this cluster number 1, this doesn't mean that this cluster is going to contain all all the observations that have a label of 1. So then you can have, for instance, for this cluster, for cluster number 1, you can have in the true label, let's assume that in cluster number 1 you have 100 points. The first point that belongs to that cluster maybe is digit number 5. The other is digit number 1, the other one is digit number 1, so on and so forth. So then, if you want to test how good is your cluster algorithm, then you first need to assign or to know which label belongs each cluster to. So in this case, how you do that? So okay, what you do is just to get the mode of each of the labels of the observations that belong to one cluster. So for instance, for cluster 1, for this one, maybe the majority of the points have a label number 1. So that cluster means that belongs to digit 1, and so on. Is that clear, guys? Yes? Okay. So then with that, you could say, okay, so with that you can say, okay, you can get an error between, okay, between the label that contains each cluster, or the label assigned to each cluster, and the true label of your digits. And in this case, we got an accuracy of 69%. So this is, I don't know if it's good or bad, because we would need to establish a baseline model, as John said. But in my opinion, no, I wouldn't be happy with that accuracy, to be honest. I think that we can do better. So how would we get a higher accuracy? Remember, we have a dataset of 64 pixels. So one thing would be to reduce that number of pixels. And then if we reduce the number of pixels, our vector is going to have less dimensions, meaning that the observations won't be that scattered. So for the clustering algorithm, it will be easier to just get or to pick up the clusters easier. Okay, but first, for the confusion matrix, for that is this one. So remember, these are the good predictions, and whatever is outside is bad. So here you can see that 5, a lot of points, well, 42 points are labeled or predicted as 9. So yeah, that is not good. So then we are going to reduce the number of dimensions, There are, again, several techniques for that. One of them is PCA, but there is another one called TSNE. And the only thing you want to know about it is that in PCA, you reduce the number of dimensions by taking into account linear relationships. But for this algorithm, you don't need to. And most of the time, the relationships of your data are not linear, so it's better to take a non-linear approach. So here, again, we use scikit-learn, and we import that algorithm. We want to have two dimensions, so we are going from a matrix of 64 columns to a matrix of only 2 columns. So this is what we are going to do here. And now the data set, the input for the clustering is going to be a matrix containing each row as an image, and instead of having 64 pixels, we have 2 dimensions. And these 2 dimensions is a nonlinear combination of the original 64 features. Again, we run the k-means clustering with 10 clusters, and then we can see that here the accuracy of, well, we do exactly the same thing. So for each cluster, we assign, we get the mode of the labels, and the mode of the label is the target that is assigned to a particular cluster, and then we compare that assigned target with the real target, and then we got that the accuracy is 93%. And now this accuracy is much better. So what is the main message here? And you can see here the matrix. So what is the main message here? That if you want to understand a little bit or more your data, you can use clustering. To use clustering is very good to reduce the number of dimensions in your data, also for a supervised learning. And yeah, basically you can use also clustering as an initial exploratory phase. If you have a project, you got some data, you need to answer one question, you can just use clustering just to understand your data a little bit more. And I've talked to people that they are domain expert in their own knowledge, and they even use clustering to just unveil relationships that maybe are not that trivial. So you guys, in your topic, you know a lot about it, but clustering can literally help you just to unveil something that you might be missing in your data. So as another example of clustering, and this is a sort of out-of-the-box example, is to do image compression. So image compression means that if you have a high-resolution image that contains a lot of colors and is very heavy, you can use clustering just to have the same image, but just less heavy, with less RGB colors. So we are going to use this as an example, nice picture of a temple in China. And if you download or if you see the data, is an array that contains the height and width, and each pixel contains a particular combination of RGB colors. So this is the shape of your matrix. So basically, you need, in order to apply again the clustering, you really need a 2-dimensional matrix for that. So in this case, since we want to reduce the number of colors, now each pixel is going to be one observation in your data set. And each RGB color is going to be one feature in your data. So this is going to have RGB. So for one pixel, you have one value of red, green, and blue. This is for pixel 1. for pixel 2 is the same. And the same holds for all the pixels in your datasets. Okay, so since you have a lot of pixels, well, this is not a lot, but okay, yeah, it's a big dataset. You use mini batch k-means. But here the trick is that, okay, you have like 2 million colors here, which is each possible combination of RGB, and let's assume that you want only 16 colors. So the number of clusters, you are going to cluster your data points such that you have, instead of 2 million colors, only 16 colors. So what you are going to do is just to specify in your clustering that you want 16 clusters, which each cluster is one color, and then you feed your data set, your image of China, the China temple, and then you just run it and you get your clusters. So if you reshape your the outcome of your clustering algorithm, you are going to see here the output. So basically, what is nice of this example is that you are not going to lose any important information in your data. So still you have less colors because this image will contain 16 colors, but still you can specify, or you can see what is the sky, what are the trees, where is the temple. So this is very good, and also can be very useful. I don't know if you have an image like your image, just to compress them. Clustering also can be very useful to do image segmentation, because then you can say, okay, which pixels can belong to a particular class. So then you can have 4 different classes, but then you don't want, well, you can do what just said, paint and draw the lines, or you can just put your image in a clustering algorithm, and the algorithm is going to tell you, okay, this pixel is a tree, this other pixel is a road, or whatever, and in the end you can have your segmentation. So basically this is it, guys. I hope it was clear. If you have questions, just, yeah, speak.
Okay, so Carmen showed us how to do clustering, and a part of that was essentially handwriting recognition, clustering based upon an image, essentially. Now, convolutional neural networks are essentially a tool that is used to look at images, and it is a series of essentially mathematical manipulations on an image or on parts of an image, which we then use in a typical neural network. So what do I mean by that? I should go through this in some logical order. So in this line here, we're loading the minced, I don't know how you pronounce it, minced data set. And the minced data set is essentially a series of 0s to 9s, handwritten in various ways, in grayscale. And we load them into there. That's just our data set. And if you look at it, it looks a bit like this. Really bad handwriting. If someone could tell me that's a 5 and not a 3, I really don't know, but it's similar to what Carmen was using. Okay. I want to see the bit. So what we do with this data set is, and this is a part of just cleaning it up and stuff, is we so we need to build a neural network which will handle these images, and these images are have got a height and a width, like Carmen was saying, and a number of matrices. So in Carmen was showing that in the image you have R, G, and B, so that's 3 matrices for each color. In this case, we have 1 because we've converted from a grayscale image to black and white. Because the reason being in this case is that do we really need to know the colors to identify the actual digits? We don't really, you can tell all those digits. Color doesn't really matter in this case. So you can go to a binary image. So that becomes a 1. So it's a 1D array of 28 by 28 by 1. These are 28 pixels by 28. And so that's our data set. And each of these are labeled. So unlike in Carmen's case, where there is a label for you to test against when clustering is unsupervised, in this case, each one of these has been labeled already. So it's supervised learning. So we're going to give a neural network, a type of neural network, a CNN, a convolutional neural network, these images with these labels. And we're going to learn to get from this to that digit. So, this first part of the workbook is about structuring the data correctly and into the structure that our code wants. We also here, because any image, whether it's 1 or multiple, is usually between 0 and 255. So to get it into black and white, we divide it by 255 because that's the number of that's 32-bit numbers, integers. So instead of it being a number, an intensity of grey between those values, if we just make it an intensity of So maybe I have kept this in grayscale and not black and white, but you could equally go to black and white. So yeah. Okay. So that's just basically that's just the preparation of our data set. But one other thing we have is that our labels can be considered one of two ways. It can be considered as an integer, but it can also be considered as a category. So for instance, you could either label it 0 to 9, or you can essentially do what's known as, I think I've written it down, let me guess, one-hot coding. And what that means is that you have a matrix whereby you have 0 to, well, there's 10 digits. So we have 10 columns. And for each occurrence of the label, so if it's 1, there'll be a 1 in the 1 column. If it's a 0, there'll be a 1 in the 0 column. And all the others will be 0. So it's like a binary representation of your category. Okay, you with me on that one? So this time, we're not trying to predict a number. Well, we are, but we're trying to predict which of these 10 categories the digit falls into.
John, to use the CNN is necessary to do that encoding, or if you
no, you could try it with 1 to 9, but then you'd probably end up with you'd put a digit in, and if it's not quite sure, it'll go, this digit is 8.8. Or I'm 90% sure it's, well, yeah. It's not, you have to do it in this kind of binary style, or else you would get, you get an actual value other than this, so you need to, can you understand why I've done that? Because this digit here, if it's making a prediction, it'll think, well, okay, the label is definitely, what's this, 0, 1, 2, 3, 4, 5. That first digit you had was number 5. It's got to be 5. So we're trying to predict that it's in category 5. But if we did it by its number, potentially it would predict that that number 5 is, well, it looks a bit like an 8. So it'll add a bit of the 8 on, and it'll add, and then you'd end up with a value like 6.73 or something along those lines. We need a definitive set, and this is it. This is the categories. Okay, so we've got our label data in categories. Now, what do we do with our actual input data, the image. So we've processed that image. Now what a convolutional neural network does is it tries to identify the features within the image that are important for defining the image. I think that's quite safe. There is certain ways that the number 7 can be defined. It has a number of straight lines horizontally, and it has a corner there, and there's a similar corner there. And so what a convolutional neural network does is break down the image into smaller parts and tries to identify which of these features are important for the image. And it does that via a convolution process. And this is a convolutional layer. And what we do is, this GIF is an example of it. It takes a smaller, what we call a kernel, and it has multiple versions of this. And it goes around, and it just simply multiplies out with some weighted values. Stop moving. Weighted values through it, and uses that template and moves over. And over time, the weights that are adjusted are is that multiplication, is that transform in just that square. So as this moves across, like this, it produces a smaller matrix. And that smaller matrix defines the features, the spatial features going through there, according to that sort of matrix that goes across the transform matrix. It's just the sum of, by the way, it's the sum of them all in substance. Okay, do you kind of get them? So, if you apply a convolution layer several times to a big image, you would get down to a very small definition of your features as a matrix. It would be kind of, it's a bit like compression. You're compressing it down to a very small image, and that defines what the rest of your, that kind of defines the features that you need. And in the learning process, by changing these weights in here via a learning process, it identifies those parts that are the most important to it. Is everyone with me? Because this gets even more important later on. Okay, so we call this, once we do this, a feature map. And we do that, each one of those passes is considered one feature. So we do that kind of 32 times, or however many times, to try and identify as many kind of features as we can, which are important. So, and they're called, each one of those is called a kernel. So what we've done here is we start our sequential model again, like we did with Keras before, and we define it. We then can use these layers. So we import here Keras layers, convolutional, and in this case we've got 2D. You can have 1D, 2D, and 3D convolutions. So essentially that, if you can imagine in 1D, it's essentially, well, it's kind of 2 points or however many points moving through a 1D piece of data. In 2D, it's a 2D thing moving, and 3D, it's a block moving through the data. And one of the other things to build up these feature maps is that we do what's known as pooling. So here, I'm sorry, I should say this. In this line, we're using 32 of those kernels. We're saying we're having our convolutional template is 5 by 5. So that's what moves through. So every time we move through it, we lose 2 of the dimensions, essentially. And the input shape we have is our image, which is now 28 by 28 by 1. And the activation function we're using is ReLU on this layer. So that's how we how these are activated, the actual okay. And then what we do is we pool the data together, because obviously we have lots and lots of them in multiple dimensions, and we want to kind of bring it all together and reduce the size even further. So we do things in each layer whereby we do what's known as max pooling. So we take groups together, so we're not moving it, there's no overlap in this one, they're together, and we make again a smaller pool of the data. So we've done we're using two operations, a convolutional one and then this pooling one, to essentially give us feature maps which define what each of our images looks like, and which we can handle, because we can't, in the case Carmen does, is that this is the same thing as where she goes from being an image of 64 values to being an image of 2. So this is our way of reducing the dimensionality of the problem. And we do it with this moving template and then this pooling. So these there's two typical ones you see is averaging, where we take the average value, and one where we take the maximum value. Because sometimes you want to know what the dominant feature is, for instance, in this one. And in this one, you want to know what kind of the common feature.
You do P90 pooling or whatever. I mean, you're now taking the outliers.
Yeah, you in these things you can do whatever pooling comes to mind. Typically, we use max pooling in convolutional for image processing.
So then you do this multiple times until you
Yeah.
get to a smaller and smaller image.
Yeah. So in this particular example we're doing here, we just have one convolutional layer. But when we go to, hopefully in the next 15 minutes, we go on to the next example, there we put them together and we compress it, and then we actually try and uncompress it with our answer. So that's what's coming up to get to the segmentation. So here, this line is here the max pooling that we have. So in order it goes convolution, max pooling, and then we use dropout. Dropout is another technique for trying to stop overfitting. So it's often good practice just to have every layer of a neural network to have a dropout. And then what we do is we've got our image. We've essentially made it smaller and smaller and smaller. But remember, when we were making it smaller, we were also adding more dimensions to it. So we had 32 of them. In this case, we had 32 kernels. So what we ended up with is a 12 by 12 by 32 matrix. So we had essentially 4,608 elements, which we then just flattened. So basically it's now, we've taken it from being a multi-dimensional into just one long vector. And now that one long vector, we input directly into a simple standard neural network. And at the end of that neural network is the output that we had before. So here we flatten the data, simple flattening command. And then, as I told you before, we should have, it's a categorical analysis. And the best activation function for multiple is the softmax, because it gives you the probability of it being in any one of those classes. So we take those 4,608 inputs, we put it into a simple 128 neuron neural network with a ReLU activation function, and then we've got 10 categories, so our output must have 10 nodes, and the activation function is a softmax. So what we're essentially trying to do is work out the probability of it being in one of those categories. Right. Then we compile the problem. We're using the same optimizer, Adam. Again, you can play with that to see how quickly you can converge to an answer. The metric, again, is accuracy. Remember what I said before, we want to know whether it's either right or wrong. So accuracy is our best measure. And this time we go for a cross-entropy but categorical. Last time, if you remember, we went for binary because we had 2. This time we've got 10, so we need a categorical loss function. And if you, after compiling it, you can ask for a summary. And this summary here shows you what the neural network looks like. We have one convolutional layer, which is, yeah, it accepts, I don't know where the 24 by 24 comes from. Then we do max pooling, and the max pooling we did at 2 by 2, so we reduce the size again down to 12. And then we use our dropout, and our dropout is just saying, what the dropout does is every time we update the weights, ignore 20% of them. We said 0.2. What we're doing is don't update randomly 20% of them each time you update. That way we stop overfitting a little bit. And then we flatten it, so those 12 by 12 by 32 become a matrix, just a vector of 4,608. Our first layer of the simple neural network reduces our output to 128 values, and then our next layer reduces it to 10. And we're trying, the number of parameters, number of weights we're trying to optimize is 592,000. So that's what that Adam optimizer is trying to essentially solve a minimization problem with that amount, 500,000 parameters. The thing is what we've done in the previous layers is we've looked at features. Now those features may act in combinations together. So for instance, if you look at our 7 and go back to our 5 or our 2, that and that are alike. But that in combination with a curve gives us a 2. So you need to then look at those features separately and Okay. And also with those there are techniques to visualize those features that you're getting out. So if you look at, for instance, what Google does with their automated cars, looking at signs, you can see at what features are really important to detecting those. And so there are techniques for seeing what your important features are through this. Okay. In our training data, we had 70,000 digits, and again, we just do the model fit. I've done a really small. I've only done 10 epochs. The reason I can do it in 10 epochs is because I've got so many samples, 60,000 to, I've probably got a very balanced data set. I've got at least 6,000 of each digit, or 7,000 of each digit, so it's quite covered, the data set. So I can probably do this in a lot smaller epochs. The batch size is quite important because that shows you kind of how often these are updated. So essentially every 200 samples it updates the weights. And I should say the verbose term basically means what output are you going to get. If you have verbose 0, it doesn't put anything out. 1 puts a bit of data out. 2 puts full data out. So here you can see when I started off the first epoch, my accuracy was pretty high at the very start, and it was pretty high on the validation data. And I did it for the 10, and by the end, I'm at 98.91, so I'm only wrong 2% of the time. So you look at what our network error is, and it's 1%ish, is what they're saying. It's 1.09. And then we can make a prediction of a number. And what I did, if you look in the data folder, that it comes with this worksheet, this notebook. There's an image, and you feel free to draw your own digit and make a prediction. I think, if I remember rightly, let's go. Where did I put it? 5.
You drew 5.
Did I draw a 5? Okay, thank you. then let's just look at what the prediction is giving me. The example here is, again, this one actually, the 7 and the 2. It makes a slight issue between the two, because if you imagine that you were to cut this off here, or you drew it quite badly and roughly, the components of the 7 kind of look like a 2. And so that's why it's saying here that it's 90-something% certain that the digit I had was 7, and it's like 10% iffy about whether it's a 1. Okay, well that's all well and good. We've done an example where we've looked at digits. Now those digits, yeah, handwriting recognition maybe doesn't come into our jobs that much. Particularly in this particular example, it's not it's not something we do every day. But what else can convolutional neural networks do? And one of the things is it can do kind of estimation exercises for you. So what is the land coverage of a particular image, or what is something, what in that image, how much of it, some physical measure, so like a regression from an image, how much of that image is used for something, or how much of it is a certain color. So what we've done here is I've created a generator. I hope most of you are familiar with generators in Python. A generator is essentially a function that you can keep asking for the next result from. And so in this while loop that lasts forever, it pumps out answers again and again and again and again. And this one is pumping out images like that. And all I've done is randomly selected, I give this a certain value, and I'm guessing here the yellow part is where I say is a particular area value. So in this case, 67.9 or 68 column. And so each time I ask for some input data, it gives me this binary image, 0 and 1s, and it gives me the percentage of the area covered by yellow, by 1. Okay, so this is kind of land usage, and I want to train it on this. So this time, instead of putting that categoric information at the end, I put the actual list number, and I can also scale it between 0 and 1. And what it also means is that I can change that very last. So this is what the previous exercise looked like in one go. And instead of having those, instead of having this last one, this last layer as being a softmax, I think I had it in the last one, I can make it linear. In fact, yeah, I'm being lazy and not even scaling that 100%, that is the value. I'm not making it between 0 and 1. So I make it linear, and the other thing I have to change is that my optimizer, my loss function, should I say, has to be, it's not categoric anymore, it's a measurement, it's a continuous measurement, so I'm going to use, just for sake of it, mean absolute error, and the optimizer's Adam. This time I have lost the accuracy. That's just my choice here. It still works, obviously, being accurate or not, but the fact is that I'm going for a value now, not whether something is or not. So it's the loss that we're concentrating on this time. The reason I use the generator for the data is because before we used fit, and what fit did, the function fit, is it worked on data that was already in a variable. But if you use fit generator and then say point it to a Python generator, this functionality will just keep calling the generator. So you can do, if you've got a numerical model providing the data, you can do it infinitely with infinite number of parameters.
What exactly are we trying to predict here?
So you're trying to predict the area that is covered by yellow in this case.
We say we know that it's always 67%?
No.
Okay.
So when we generate it, we randomly generate it with between.
Yeah.
It's just randomly both,
Generated.
and
Yeah.
then we count them in that generator,
Yeah.
and we get a label which is the percentage, and we get the image,
Yeah.
and that's the input and
Yeah.
the label and the input,
Inputs.
the
Okay.
features.
I got it. Yeah.
Okay. And what you see is when we first start loading, so we did 10 epochs, 10 steps per epoch, so that's how many times we go back to the generator to get more data. And yeah, verbose 1, I don't want all the details this time. And what you see is that at the first stage, it was 68% wrong. But by the time we get to the end, it was round about 3% wrong on that data set. And if we look at it now, that was the history of its learning process over the epochs. I evaluate the generator and it's saying, yes, your error is around about 1.5%. And now I've done some things where I take a square, for instance. We never taught it on a square or a shape. We taught it on a random distribution. And you see that, so the areas here, we get a reasonably close estimation of it. Now you can imagine that if you're using satellite data, for instance, and that's a tile, and you want to know the amount of ground usage based on a pixel, this becomes very useful to be able to give you percentages very quickly. They are an estimate, but these estimates are over great areas will average out.
Okay. Yeah.
But the thing is with the convolutional network is, if you can imagine that it will work pretty much with any size, because that the input kind of goes through everything and makes it into a particular size.
Yeah.
So it's kind of generic on what size you do it. It may becomes a lot longer to run, but the training might be a lot shorter if you break it down into smaller. So now if you open, and this is where we're basically, we're good for time, considering you guys learnt that in about 35 minutes. We're going to look at segmentation, which is essentially what Joost used for his problem. And we're going to use a very practical exercise on segmentation. So a lot of work has been done very recently with segmentation in AI, deep learning. And there's kind of 4 areas of it you can see. You've got image classification. So this is your typical, what is in an image? The whole image. How many cats are in it is typically, you know, I think, is there a cat present? Is there a dog present? The other one, we went further and said, where are those objects? Can we locate them? And so what we do is we actually locate the area where it is. And then we went further and went, well, we want to do semantic segmentation, which is where we want to know what pixel belongs to what object, precisely. And so you get these sort of elements where we say, yeah, we know that pixel belongs to a cube, but we don't necessarily know which cube. So those 3 cubes, we don't know the difference. We certainly don't know the difference between them 2 cubes. We just know that they're pixels in cubes, and that's all we're saying. And then we're trying now more and more to go to this instance segmentation, where it's to say, essentially, that's a cube, and that's a cube, and that's a cube, and all 3 of them are different, and we know they're different, and we know their locations are different. So it's pixel. At the moment, we see what material it is, and now we're going to what object is it, what actual instance of an object is it. So that's where we're heading, and what I'm going to show you today is this one, the semantic segmentation. Yeah, definitely. I couldn't teach you that one in 35 minutes. So. Okay, so I'm going to teach you via an example. And the example I'm going to use is an example of trying to find the cell walls from microscopic data. So this is I don't know what it is precisely, some biological something made up of cells and nuclei. And what we're trying to do is work out these boundary conditions, where these boundaries are between them. And on the right, somebody has painstakingly drawn where they are, or they've used maybe a clustering algorithm, maybe, or they've used some sort of Photoshop to say where all these boundaries are. And so we've got, that's the original, and that is what we want on the other side. So instead of this time we pump into some network an image, and on the other side we get a number or a category or a percentage or a probability. This time we're going to pump in on the input, we'll pump in an image, and on the output we're also going to get an image. So we're going from an image to an image. And one of the key ways we're going to do that is using an encoder decoder or an autoencoder, we call it. And what that does is, before, when we spoke about the convolutional neural network compressing the image via features, we compress the image via features and then we blow it back up again back into an image. So we get down to that image size. We now know the parts of the image, the parts of the features which are really important, and then we blow it back up to just give us the features at the other side. So that's kind of the way it works. And so let's have a look. So we'll start with our data set. Our data set was some 512 by 512 grayscale images, but we will limit it to 30 of them. It's all we have in this data set. So we've not got many. So what can we do to make a bigger data set? And one of the things we can do is divide it into tiles. Reality is that we're just trying to detect the cell membrane and the cell wall that we see in the slide. So do we need to do that across a whole image, or can we just take a part of the image and do that? And then when we input into this, we can take multiple tiles and input it through. The other thing is that does the orientation of our images matter? Doesn't, because reality is the cell wall is the same no matter what angle we put it at. So we've got 0, 90 degrees, 180 degrees, 270. So we can go all the way around, and that essentially is 4 images. So by splitting these images into, we're going to have 64 by 64. So we've already increased our by 6 by 6. How many times does 64 go into 512? 8. Oh, thank you. So we've increased it by 64, one image by 64, and each one of those 64 can be rotated 90 degrees, and 90 degrees in that for 4 times. So we've increased our and we've got 30 of them. So from a data set of 30, we've got a rather larger data set. And what you see here underneath, and there is also flipping. You can mirror the image in all the directions too, in the vertical and both ways as well. So you use lots of ways with images to get lots of more data from a single image. Okay, so this is essentially preparing those files with the flipping and the twisting and all that to give us, again, a data set that is a little bigger, quite a lot bigger actually. I'll let the party. So this, I've just randomly taken one here. If you press play, run on your thing, you'll get a separate image. But this is the ground truth against that image zoomed in. So that's one of those tiles. And of course, it's also probably been twisted and okay. So we've got our data now. We've trimmed it and got a data set that's big enough. Oh yeah, that's the number we've got. from 30 images, we got 1920. And I don't think I flipped it in all directions. I think I just flipped it horizontally. So we're already quite high with how many we've got. Okay. Now this is a encoder-decoder. In its purest sense, it is a series of those convolutional and max pool layers put together until you get it to a very small size, and then you blow it back up to get your prediction. That is it in its purest sense. But what we're also able to do is connect these layers together. So the input here also is the input there. Input plus these features. And that way what we're able to do is maintain the initial structure of the image throughout the network. But this is the basic one that you should really know about, which is the encoder-decoder, which goes small and then builds itself back up. And the way it builds itself back up is by, and I'll show you, well, that's another representation of the convolutional network that I showed in the previous example. But then this is how we build up in the decoder. We do the opposite of convolution, which is to kind of, we're able to produce, so this is producing from these areas, with blank areas bigger space. So it's just zooming back out by using, so this is the input and this is what you get out. Okay? So it's just the opposite process. And then, as I said, there's enhancements where you connect these pooling layers together. So you combine the input here with the input here, the output here, sorry, with the input here to be the input to this layer, and that maintains some structure of the image throughout the network. Okay? Yeah, so you can imagine this is just one. And it's just repeated a lot, and then this is one that's repeated a lot. And that's precisely what we do when building the kernel, building the model, sorry. So here we're going to use the similar modules. Our input size now is 64 by 64 by 1, because it's a black and white, a grayscale image. Here we have to use a slightly different terminology. We're not using we're using a TensorFlow terminology for building a neural network. The old one was sequential. So basically the output of one layer is the input to the next layer. But here we've got connections between layers. So there's a layer earlier that we want the output of going one much later. So we have to build it. We have to build it in a slightly different way, and that way is that we declare a layer in a similar way. So number of kernels, size, the activations function. This padding basically saying that I want the same size going in and out. So when it's trying to make it smaller, it actually just puts zeros around the outside. And what actually happens is it's this pooling exercise here that's making it small in this particular case. But anyway, and what we say is our input is what's in the brackets afterwards. So we make a convolutional layer 1, and its input is inputs, which we declare there. And then we do another layer, another convolutional layer. This has 2 convolutional layers for every pooling layer. We then put the input to this layer as being the previous one, so conv1, and then we do the max pooling. So that is one single convolutional layer for our encoder. And then what we do is so that's what I mean by the padding. You see that it does the same. by putting this padding around the outside, we produce the same size image as the input, but we just have zeros around the outside. Yeah? But then we want 3 or 4 of these layers. So we do it again, but this time the number of kernels doubles. So as we go smaller, we double the amount of features we're trying to detect. So in this case, 16. And the input to this is the output from the last one, so pool 1. And we do the same thing. Again, we do it again, but this time we double the number of kernels, so we have 32 in each of them. And then we do a 4th one, 64, then a 5th one. So we've now got 128 kernels and a very small x by x kind of array of them. So we've got a load of feature maps, highly compressed, but we've got 128 of them. Okay? Right, now here's where it gets a little more complicated. We do something called upsampling at this point, which is that's how we're blowing up our image with convolution as well. So we do a thing called upsampling, and I think I describe it below somewhere. No, I don't, sorry. So upsampling is a way by which we're trying to blow it up by each size, because obviously we've reduced it by 2 by 2 by 2 by 2 on each level. We now need to go back up 2 by 2 by 2. So we use upsampling in those 2 by 2s. And then we do the convolution again. And this time we take in that upstart there, that size bigger. But what we also want to do is merge that image with the corresponding image in the encoder. And that's what we've got there, the convolutional 4. So those have just merged together into one combined matrix. And then we do more convolutions. What you're actually after is in very complex images, you've got a lot more features to try and detect. So therefore, what you want to do is, so essentially we're doing a feature map of a feature map of a feature map. So the actual features are a bit more complicated to understand. It's not like here where I'm just saying lines give me an answer. I'm trying to kind of, it's a lot more complicated. So I think the more complicated it is, the more convolutions you have to do to be able to detect the features that you need.
Oh, okay.
That's my explanation to it, and I'm sticking to it. Okay, so you repeat that a lot, again. The upscaling, pulling it back up together and doing convolution at the same time. Sorry. So we do all the decoding, yep. And then, amazingly, we then want it to be, we then put it through, again, a standard fully connected neural network. This time, it's, wait a minute, I'm at the right point. I should be, no, actually not standard. I put it through the convolutional neural network again. But the very last one, I want one value. And the reason I want one value is because it is a pixel. It is the pixel I'm doing it for. It's not anything else. But by this time, it's full size. So this time it's doing. It's got one. The kernel. It's got one of them, and it's one in size. So if you imagine it, it goes across the thing, and it's just one pixel again. So it's recovering the full image, and it's saying I've used sigmoid because it's either going to be black or white. Or, yeah, black or white. So that's why I've used sigmoid there. Then, this time we compile it very similarly with model compiled. We put together our inputs and our outputs, should I say. Then we want, it's black and white, so we have the binary cross entropy. And this time we go back to accuracy being our measure, because it's a categoric thing, it's either right or wrong. And Yep, you can train it with that generator again, so you use this, and this is the generator we wrote at the top. And feel free to be running this. Has anyone run it yet? Still running?
No, it's the 8 epoch.
All right, at 8
It's like 1 minute each.
Okay, so you've only got 2 to go.
Yeah.
Okay. Anyway, I get up to about 90% accuracy, 91% accuracy. And then if I test it, and I do believe there is an error in this code at the bottom that I've not corrected, so please find it. That's the that was my little test, or more my laziness probably. And then my prediction is here in this little chart. I put in this original image, these original images. These are the ground truths. So this was a ground truth for that. But the prediction, if you look, the prediction of this tries to reasonably get the shape. Misses a bit out there, and you can see here it's having a little difficulty, but it's a pretty close thing. Jost's team did it very similarly. They would have had different materials properties they wanted to see and detect. They would have also done the water, for instance. So their output ground truth would have been a line, perhaps, out bordering the water.
No, we're also putting out all the pixels and then detecting the water interface with the air.
Okay. No, but I'm just saying, what is your ground truth?
Oh, the ground truth is also for every pixel the.
Just what the material is.
Yeah.
Even for,
just
even for
the
the one with the line?
Yeah, with the line, there's a script in between that detects the line, and I know that air is always on top of water, is always on top
right,
of...
okay, so it's post-processing that gives you the line.
It's a bit of post-processing.
Yeah, okay.
But you look at Jost's case, and those videos of water and air, the interface is pretty difficult to see in those lighting conditions. And so, yeah, I can. But the thing is, again, if you can't produce the ground truth, then it can't be taught into the machine. So, yeah, I still disagree that this here. I still think the prediction we make is far better than the ground truth that it had. Although that might have been completely white, because it's the way it's plotted is if there's only one number, it just does black. So it's possibly not detecting anything. So what it may have been saying is that might be a nuclei, and then so this I am wrong, or the prediction is wrong. So this may have been better if we label nuclei one color and done the test that way. But what I wanted to say earlier is the way Jost's team did it was you can get an off-the-shelf system that's been trained on lots and lots of images, and what they do is then they take all the layers of the system that has been pre-trained and delete the last layer. Because what we see is that it's the actual last layer that does the pulling together of all the features and all the colours and etc., and does the actual classification of a pixel. So you can take a highly pre-trained data set model, and then you just train your network on that last layer. You put your bolt in a completely blank layer with some random weights and just retrain it a little bit, and you get far better results, and it doesn't take as long to do. Yeah, so what we're saying is that all those convolutions are trained to, are basically there to detect features in your data. And it's only when you get to the last couple of layers that it starts piecing those things together to make its decision. And so things that have been trained on huge data sets know how to detect lots and lots and lots of different features in the data. And it's only bringing those different features together that actually answers your question. So what we say is that all those layers we really need to detect the features and pull the features out of it. It's just the fact that we're looking at different objects than cats and dogs and cars and brain tumors or whatever is in the algorithm, and we're looking at water or subsurface materials. Okay, thank you. And, if you have any questions, then you know where to find us.